The world, as we experience it, seems to follow a set of reliable, comfortable rules. An apple falls to the ground. The sun rises and then sets. A fire warms and then fades. We are born. We grow old. We live in a world of reassuring certainty, built upon a foundation of perceived simplicity. We have, for millennia, found comfort in this predictable rhythm. We have come to believe that what we see is all that is, that the three dimensions of space, up, down and across, and the relentless ticking of time, are absolute, unchangeable boundaries of existence. Our everyday lives confirm this. We move, we measure, we interact, and the laws seem steadfast. But beneath this placid surface, beneath the scale of our senses, and out in the vast, silent depths of the cosmos, lies a hidden reality, a deeper dimension, a world where our most fundamental intuitions are not just challenged, but completely, irrevocably shattered. This is the world that can only be revealed by looking closer than the eye can see and farther than the imagination can stretch. A realm so utterly strange, so profoundly counterintuitive that it seems to border on magic, yet is ruled by a cold, elegant logic. This is the true landscape of the universe. A world governed by laws so strange and so subtle that we are only just beginning to comprehend them. This is the world of physics, and it is perhaps the most magnificent and most misunderstood landscape in all of human discovery. In this journey, we will venture beyond our common sense to explore the great enigmas of our time. We will seek to confront the true, bewildering nature of existence itself. We shall leave behind the simple Newtonian stage of our childhood and enter the grand, flexible theatre of the cosmos. We will begin by reimagining the very ground beneath our feet. We will discover that gravity is not a force at all, but a profound, silent warping in the flexible fabric of space and time. We will then dive into the ghostly heart of matter to witness the spooky miracle of quantum entanglement, where two particles separated by an entire galaxy remain bound by a single, instantaneous and invisible thread. Our voyage will take us to the grandest scale into the cosmic darkness. We will hunt for the invisible dark matter, the scaffold that holds our galaxies together, and confront the mysterious dark energy, the anti-gravity force that is pushing our entire universe to a cold and accelerating fate. We will challenge the very nature of motion by exploring the universe's ultimate law, the speed of light, a barrier that bends time, shrinks space, and stands as the silent guardian of cause and effect. And finally, we will confront the most intimate and most relentless law of all, the arrow of entropy, the force that gives our lives direction, that powers our very sun, and that dictates the final silent end of everything. This is not the universe we thought we knew. It is a place of hidden connections, invisible majorities, and profound, elegant laws. A place of staggering, humbling wonder. Our journey into the real cosmos begins now. For as long as humanity has gazed upon the world, one force has held us captive. It keeps our feet firmly on the ground, anchors the oceans to their beds, and commands the majestic, predictable dance of the planets above. We call it gravity. We feel its pull, its unwavering presence. It dictates the weight of every object, the shape of every mountain, and the scale of every cosmic structure. It is the invisible architect of the cosmos. But what if I told you that our understanding of this fundamental force, this invisible embrace, has been profoundly, beautifully, and astonishingly incomplete? For centuries, we believed gravity was a simple, irresistible pull. A force at a distance, as Isaac Newton described it. A colossal, invisible hand reaching across the void, tugging at every atom with a strength precisely proportional to the mass of the objects involved. It was a revolutionary idea for its time, and it explained so much. It allowed us to chart the paths of planets, predict eclipses, and even use mathematics to discover new celestial bodies through their gravitational influence on others. The cosmos became a colossal, beautiful machine, governed by simple, elegant rules. But the universe, as it turns out, is far more subtle, far more intricate, and infinitely more elegant than we ever dared imagine. Newton's genius was undeniable, but a lingering question remained unanswered. How exactly did this force travel through the emptiness of space? What was its medium, its instantaneous messenger? If the sun were to vanish instantly, would Earth know immediately? Newton's description worked brilliantly, but it lacked the crucial mechanism. Today we journey beyond the simple pull. We journey into the very fabric of existence, into the interwoven tapestry of space and time itself. We will discover that gravity is not a force, but a profound deformation, a cosmic waltz orchestrated by the heaviest dancers in the universe. At the dawn of the 20th century, a young patent clerk named Albert Einstein offered the world a new paradigm. His theory of general relativity didn't just refine gravity, it utterly transformed it. He proposed that space and time are not separate, rigid backdrops against which events unfold. Instead, they are inextricably linked, forming a single dynamic four-dimensional entity, space-time. Imagine space-time as a colossal, invisible rubber sheet, stretched taut across the cosmos. When there is nothing upon it, a small marble representing a planet or a ray of light will roll across in a perfectly straight line. This is the path of least resistance. But now introduce a massive object, a star, a planet, and the sheet deforms. It creates a dent, a warp, a curvature, and it is this curvature that we perceive as gravity. The small marble, our planet, isn't being pulled by an invisible force. It is simply following the curves in the fabric of space-time created by the more massive object. It is, in fact, always trying to move in the straightest possible line, but the line itself is bent. Light itself, the fastest traveller in the universe, is not immune to this curvature. It too follows the distorted pathways, bending its course around colossal masses. This phenomenon, known as gravitational lensing, allows us to see galaxies warped and magnified by the unseen space-time lenses of foreground clusters. This curvature is the majestic geometrical truth of gravity. It was a conceptual leap of breathtaking audacity. Gravity, the force that binds us, is merely the universe's elegant geometry made manifest. Einstein's space-time is not just about space, it is also about time. And one of its most profound and perhaps unsettling predictions is that time itself is not absolute. It flows differently depending on your proximity to massive objects. This is time dilation. Clocks tick ever so slightly slower near a massive object where space-time is more deeply warped. Stand on the top of a mountain, and your clock runs infinitesimally faster than a clock at sea level. The effect is tiny, but utterly real. Our global positioning satellites, essential for navigation, must constantly adjust for these relativistic effects. They travel faster than us, which slows their clocks due to velocity, an effect we will discuss later, but they are also in a slightly weaker gravitational field than us, which speeds their clocks. Without accounting for the precise balance of these factors, GPS systems would quickly become useless. Time, it turns out, is a negotiable elastic component of the universe. But where does this curvature lead when taken to its most extreme? To objects so dense, so massive, that they tear the very fabric of space-time into an infinite abyss. Black holes. Imagine a region where the space-time dent is so deep, so precipitous, that nothing, not even light, can escape its gravitational embrace. This is the event horizon, the point of no return. Beyond it, time itself behaves in unimaginable ways. All future paths point inward to the singularity. Black holes are not cosmic vacuum cleaners, but profound cosmic laboratories, places where the rules of space-time are stretched, broken, and rewritten. They are the universe's ultimate expressions of curvature. For a century after Einstein's grand vision, one crucial prediction remained elusive. If space-time is a dynamic, flexible fabric, then violent cosmic events, like the merger of two black holes or the catastrophic collision of neutron stars, should send ripples through this fabric. Waves of warped space-time, traveling outward at the speed of light, carrying with them the echoes of these colossal catastrophes. These were dubbed gravitational waves. And they are not light waves or sound waves, they are distortions of space and time itself. They would stretch and squeeze everything in their path, infinitesimally, immeasurably. The challenge was immense. To detect these ripples, we needed instruments of almost unimaginable sensitivity. The expected distortion arriving at Earth was far smaller than the diameter of a single atom. Yet in 2015, after decades of meticulous engineering and scientific dedication, the LIGO experiment achieved the impossible. It detected a whisper from the deep cosmos, a faint, almost imperceptible tremor. That tremor was the definitive proof, the very first direct detection of gravitational waves. It was the death rattle of two colossal black holes colliding over 1 billion light-years away. A cosmic crescendo that reached us after journeying for an unimaginable expanse of time and space, revealing a new, profound way to listen to the universe. This wasn't just a confirmation of Einstein's genius, it was the opening of a brand new window onto the universe. We had listened to the universe only with light, through our eyes and telescopes. Now we had the ability to feel its most violent convulsions, to hear the symphony of its heaviest denizens directly in the structure of space and time. The invisible embrace of space-time is no longer a passive stage. It is an active participant, bending, warping and rippling, telling us stories of creation, destruction, and the very laws that govern existence. Now we move from the colossal scale of stars and galaxies to the realm of the minuscule, the quantum world. The world we perceive is one of reassuring solidity, a world of cause and effect, a place where things are here or there. A dropped stone falls, a pushed ball rolls, and an object, once it leaves our sight, continues to exist, entirely independent of us. We are creatures of the local. We believe that to influence something we must touch it or send a signal to it. This is the bedrock of our reality. But beneath this comfortable classical world, beneath the scale of our senses, lies a realm so utterly strange, so bewildering, that it shatters our most fundamental intuitions. The quantum world is not a place of tiny things, but of possibilities. An electron is not a simple hard sphere. It is a cloud of probability, existing in a haze of all its potential locations at once. We see this in the famous double-slit experiment. A single particle does not choose one path. In a way that defies our senses, it takes both. It interferes with itself like a wave. It is only when we try to catch it in the act, that this cloud of possibility collapses into a single, definite reality. This is superposition, the strange, ethereal state of existing in all possibilities simultaneously. And it is this very strangeness that gives birth to the universe's most profound enigma. Imagine two particles born from a single energetic event, a pair linked by their shared origin. Quantum mechanics tells us that these two particles are not two separate entities, but rather two parts of a single unified system. They are entangled. Their properties say their spin, a kind of intrinsic angular momentum, are now bound together. But here is the miracle. In their state of superposition, neither particle has a definite spin. One is not up and the other down. They are both simultaneously in a state of up and down potential. They possess a shared fate, a collective identity. Now we separate them. We send them on journeys across the cosmos, across light years of empty void. They share no conventional signal. No communication is possible between them that is not limited by the speed of light. An observer on Earth measures her particle. In that instant, its wave of potential collapses. It chooses a state, spin up. And at that very same moment, instantaneously, its twin, light years away, also collapses. It must choose the opposite state, spin down. There is no time delay, no signal sent. It is as if the universe itself knew. Einstein, famously, was deeply troubled by this phenomenon, believing it violated the principle of locality, that a physical influence requires a physical connection. He called it spooky action at a distance. He believed there must be a hidden local explanation, a kind of prearranged script. For decades, this spooky action was a fierce debate, a philosophical puzzle. Could there be hidden variables, unknown local properties that determined the particles' outcomes the moment they were born, simply making the collapse look instantaneous? But in the 1960s, a physicist named John Bell devised a mathematical theorem, a way to ask the universe directly if this ghostly connection was real or if hidden variables were sufficient. Bell's theorem established an inequality that a local, realistic universe must obey. The experiments carried out with breathtaking precision, culminating in the work of physicists like Alain Aspect, have given us a clear, unambiguous answer. The results consistently violate Bell's inequality. The universe is spooky. The connection is real. This is not communication. We cannot use it to send a message faster than light, as the outcome of the measurement on Earth is still fundamentally random. But the correlation, the shared destiny, is absolute. It suggests a unity at the heart of existence. Entanglement forces us to reconsider what it means to be separate. This profound phenomenon is no longer just a curiosity. It is the foundation for a new technological revolution. We are learning to harness this ghostly bond in quantum computing, where we use entangled particles to perform calculations exponentially faster than classical computers, and in quantum encryption, creating communication links that are fundamentally unbreakable. Entanglement suggests that at the deepest level, the universe is not a collection of individual objects, but an indivisible, interconnected whole. It is an invisible web connecting the cosmos in ways we are only just beginning to comprehend. A silent, instantaneous thread woven into the very fabric of reality. It tells us that we live in a universe far stranger, far more complex, and far more deeply connected than our everyday senses can ever perceive. Look out into the velvet darkness of the night sky. What do you see? Points of light, stars, the glowing band of our own galaxy, and with the aid of our most powerful instruments, billions upon billions of other galaxies. A cosmic ocean teeming with luminous matter. It is a universe of staggering beauty, of incandescent gas blazing stars, the dust and rock that form worlds like our own. We have spent centuries cataloguing this light, believing that this visible splendor was the universe. The vastness of this known world is humbling enough. But a profound and humbling discovery has been made. All of it, every star, every planet, every living thing, all the matter we can see, touch and understand, makes up less than 5% of the total cosmos. The rest, 95%, is a vast, invisible unknown. A dark sector comprised of two of the greatest mysteries ever to confront us: dark matter and dark energy. The visible universe is merely the delicate foamy crest of a colossal hidden ocean. Our first clue to this hidden majority came from watching these great spiral cities of stars. In the 1970s, the astronomer Vera Rubin observed the way galaxies rotate and found something deeply disturbing. The stars on the outer edges were moving too fast. According to our laws of gravity, and based only on the mass of visible stars, the outer reaches of the galaxy should have been orbiting slowly. They should have been flung off into the void like water drops leaping from a carousel, spinning too quickly. But they were not. They held their course, orbiting at speeds that demanded far more mass than we could account for. The only explanation was that the galaxy was being held together by an enormous unseen mass. A vast halo of some invisible substance exerting a powerful gravitational pull, but emitting no light, no radiation, no detectable signal whatsoever. We call it dark matter. It is the scaffolding of the cosmos. It does not interact with light. We cannot see it. We do not know what it is, whether it is made of exotic, yet-to-be-discovered particles like WIMPs, weakly interacting massive particles, or something else entirely. But we see its profound gravitational influence everywhere. We see light from distant galaxies bending around it, a powerful gravitational lens created by the invisible mass. We see its imprint in the structure of the cosmic web, the very architecture upon which all visible galaxies are draped. This invisible stuff outnumbers all the stars and gas we know by more than 5 to 1. And just as we were grappling with this invisible mass, the universe revealed an even greater shock. For decades, we believed the expansion of the universe, which began with the Big Bang, must be slowing down, pulled back by the collective gravity of all the matter within it, both light and dark. It seemed the only question was, would it slow to a stop? Or would it one day collapse back on itself in a big crunch? Then, in 1998, astronomers observing distant exploding stars, supernovae, which serve as standard candles to measure cosmic distance, found the precise opposite. The expansion of the universe is not slowing down, it is accelerating. Something is pushing the universe apart. A mysterious, repulsive force inherent to the very fabric of space itself. A force that grows stronger as the universe expands, because as space grows more of this energy is created, driving galaxies away from each other at ever-increasing speeds. This is dark energy. It is not matter. It is a pressure, a cosmic anti-gravity that permeates all of space. It is the dominant force in the universe, accounting for roughly 70% of the total energy mass content of the cosmos. The universe is primarily composed of forces that are completely unknown to us. So this is the universe we find ourselves in, a cosmic pie where 95% of the ingredients are unknown. A universe dominated by two invisible forces, one pulling it together, the other pushing it apart. A delicate, unstable balance. The hunt is on. Deep underground, in pristine laboratories, scientists search for the faint, phantom trace of a dark matter particle passing through their detectors. Our greatest telescopes, like the Hubble or the James Webb, peer into the distant past, mapping the expansion, trying to understand the nature of this dark push. Is it the energy of the void predicted by Einstein? Is it a new, undiscovered field? We simply do not know. We are in a profound sense adrift on a tiny luminous raft in a vast, dark and unknown ocean. The discovery of this hidden 95% is not a failure of science, it is its greatest, most humbling triumph. It has shown us that our understanding is beautifully, tantalizingly incomplete. We are explorers who have just landed on the shore of a new continent, and the true vast expanse of reality lies unseen just beyond the horizon. The greatest journey of discovery has only just begun. It is the fastest thing in the universe, the ultimate messenger, a massless, timeless traveller that bridges the void between stars. We call it light. For us, its movement appears instantaneous. We flick a switch and the darkness is banished. But light travels. It has a speed, a finite and absolute velocity. This speed is a staggering number. 299,792,458 meters per second. A velocity so immense that for any earthly purpose it feels like eternity. But this speed is not just a number. It is not just a record to be broken by a better engine. It is a fundamental law of the cosmos. A barrier woven into the very fabric of reality that dictates the nature of space, of time, and of cause and effect itself. The true revelation came from a young Albert Einstein. He was captivated by a deep paradox. What would happen if you could catch up to a beam of light? If you were traveling alongside it, would the light appear frozen, like a motionless wave? His answer, born from pure thought, was revolutionary. He declared that the speed of light is constant, not just for a stationary observer, but for everyone, no matter how fast they are moving. Whether you are standing still or rocketing away at half the speed of light, you will always measure light moving away from you at the exact same constant speed. C. This simple, audacious idea has consequences that shatter our everyday experience. For if the speed of light must be the same for all observers, then something else, something we thought was absolute, must be flexible. And that something is time. Imagine a clock that measures time by bouncing a beam of light between two mirrors. For a person standing with the clock, the light travels a short vertical path. Tick, tock. But now put that clock on a fast-moving rocket. For an observer standing outside that light beam must now travel a longer diagonal path to keep up with the moving clock. And because the speed of light cannot change, it must take longer for the light to complete its journey. The moving clock from the outside perspective ticks slower. This is not an illusion. It is time dilation. Time itself flows at different rates for different observers. The faster you move through space, the slower you move through time. This has been proven countless times. Cosmic ray muons, short-lived particles created in the upper atmosphere, survive their journey to Earth's surface only because their internal clocks are slowed by their tremendous speed, allowing them to travel vast distances in their own extremely short lifetime. Time is a personal, relative experience. So what happens as we try to reach this ultimate speed? As an object with mass like a spaceship accelerates time, for it slows down. But something else happens. Its mass increases. It becomes heavier, more resistant to any further acceleration. As it gets closer and closer to the speed of light, its mass approaches infinity. To push it just that one bit faster to reach the ultimate speed would require an infinite amount of energy. It is the universe's ultimate, unbreachable barrier. This is the meaning behind Einstein's most famous equation, E equals mc squared. Energy is equal to mass multiplied by the cosmic speed limit squared. It reveals that mass and energy are simply two interchangeable forms of the same fundamental entity, forever locked in this speed constraint. The speed of light is the conversion factor. Space itself also contracts in the direction of motion. The universe, from the relativistic traveler's perspective, flattens. Time and space are conspiring to ensure that one law, the constancy of light, is never, ever broken. Why? Why has the universe imposed this strict, unyielding law? Because this speed limit is what protects cause and effect. If anything could travel faster than light, then for some observer, a message or an effect could arrive before its cause was even sent. The temporal order of the universe would be destroyed. The distinction between past, present, and future would collapse. The speed of light, therefore, is the law that preserves causality. It ensures that an effect can never come before its cause. It defines our past and our future. It is the ultimate boundary that stops the universe from descending into temporal chaos. The speed of light is not a frustrating limitation on human ingenuity. It is the very thing that knits time and space together, the metronome of the cosmos and the silent, profound guardian of the one-way flow of events. We observe in our universe a constant, relentless direction to things. A sandcastle built with care does not spontaneously assemble itself from the beach. It erodes. A cup of hot coffee does not grow hotter in a cool room. It cools. A great mountain range does not grow taller. It slowly submits to erosion. This is the arrow of time. We remember the past, but we do not remember the future. We move inexorably from order to disorder, from concentrated energy to dispersed energy. This is not a suggestion. It is perhaps the most fundamental and unyielding law in all of physics. It is the second law of thermodynamics. It is entropy. What is this law? At its heart, it is simply a law of probability. There are quite simply more ways for things to be disordered than for them to be ordered. Imagine a box of gas. It is theoretically possible that all the molecules could, by pure chance, huddle in one corner. But it is statistically, astronomically unlikely. There are vastly more ways for those molecules to be spread out evenly throughout the box. And so the universe, in its constant restless motion, simply moves toward the most probable state. It moves from states of low probability order concentration to states of high probability disorder dispersal. This measure of dispersal, this relentless spreading of energy, is entropy. It is the universal tendency toward thermodynamic equilibrium, where everything is smoothly, evenly mixed. But what about life? What about the islands of breathtaking complexity we see around us? This tree is a miracle of organization. We build cities, write symphonies, create magnificent structures. We are magnificent islands of order in a universe that tends to decay. Does life defy the second law? No. It fulfills it in the most profound way. To build this local, intricate order, the tree or you must consume energy. And in the process of using that energy, you must create an even greater amount of disorder in your surroundings. You create heat, you exhale disordered gas. You radiate energy wastefully into the cosmos. Life is a beautiful, temporary eddy in the great river of entropy. We are not a violation of the law. We are a consequence of it. We pay the price of local order by increasing the overall disorder of the universe. This constant flow of energy from a high concentration source, the sun, to a low concentration sink, deep space, is what powers all dynamic processes. Entropy is the engine of change. But this law, this relentless arrow, also points to an inevitable final destination. If the universe continues to expand, driven by dark energy, and all energy continues to disperse, it will lead to a final state. A time, trillions upon trillions of years from now, when the last star has sputtered and died. When the last black hole has evaporated, when all matter has decayed, and all energy is spread perfectly, uniformly throughout the cosmos. A point where no more work can be done, because there are no more energy differences. It is known as the heat death of the universe, a state of maximum entropy, a cold, dark, uniform, and perfectly silent abyss. A place where the arrow of time finally has nowhere left to point. It is a bleak and distant prophecy. But it is the ultimate expression of this profound law. And it reminds us that the order we see, the life we live, the very moment of now, is a precious, magnificent, and improbable anomaly in the grand, relentless story of the cosmos. We began this journey believing we knew the rules. We end it with the profound realization that the universe is overwhelmingly defined by its mysteries. We have found that the force that anchors us, gravity, is not a force, but a twist in a shared fabric. We have discovered that the tiny building blocks of reality, quantum particles, are not separate, but instantly bound by invisible threads. We have learned that our entire luminous world is merely the foam on an ocean of dark matter and dark energy, a hidden 95% that dictates our future. We have recognized that the speed of light is not a benchmark to surpass, but a sacred, necessary constant that safeguards time itself. And we have confronted the inevitable destiny dictated by entropy, the law that gives meaning and motion to our fleeting existence. The universe is not merely larger than we thought, it is fundamentally stranger. The greatest lesson of physics is humility. It teaches us that our direct sensory experience, our everyday common sense, is insufficient to grasp the truth of existence. The rules that govern the universe are far more elegant, more interconnected, and more beautifully bewildering than we could have ever imagined. And the greatest wonder of all is that we, these tiny, temporary, highly ordered arrangements of matter, have the capacity to observe, to question, and to begin to understand the invisible monumental laws that govern everything. The journey continues, the mysteries deepen, but in that deepening lies the most magnificent adventure of all.